जी सर, जी सर लाइव स्टार्ट बैक
Okay. Please sit down. Before we start, I invite Professor Dr. Nilwar Sen, Dr. Eric, Dr. Shahar Siddiqui Saab, and Dr. Khurram Shabir to come on the stage. And most beneficial, honorable teachers, and my dear fellows, Assalamu alaikum. And good morning, everyone. Today, I am most welcome to all of you in this 2 days international conference on recent developments in and applied mathematics. Let us start this beautiful day with the blessing and mercy of. So I would like to invite Khabar Abbas.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم رب المشرقين ورب المغربين فبأي آلاء ربكما مرج البحرين يلتقيان بينهما برزخ لا يبغيان فبأي آلاء ربكما تكذبان يخرج منهما اللؤلؤ والمرجان فبأي آلاء ربكما تكذبان وله الجوار المنشآت في البحر كالأعلام فبأي آلاء ربكما ربكما تكذبان آمنت بالله صدق الله العظيم.
Jazakallah. As we all know that the Prophet Muhammad
अस्सलाम वालेकुम रहमतुल्लाहि व बरकातुहू। है रसूले अमीन खातमुल मुरसलीन, तुझ सा कोई नहीं, तुझ सा कोई नहीं, है बासिद को यकीन मंजर पिलाई गई, फिर तेरी तुझ सा कोई नहीं, तुझ कोई नहीं, तुझ कोई नहीं, ए रसूले अमीन।
Subhanallah. Now I would like to thank our special guest, Professor Dr. Malak Sawar Hussaini, Chairman Professor Dr. Malak Sawar Hussaini, Chairman Department of Mathematics, Punjab University. And thanks special speaker Professor Harry, Yonsei University, South Korea. Thank you so much for your precious time. I would like to congratulate the Department of Mathematics, Government College University, Faisalabad, for their tremendous and determined and commitment to organize the 2 days international conference. Mathematics is considered the mother of science and has a wide range of applications in physical as well as natural sciences. Therefore, the conference provides a valuable opportunity for teachers, scholars, and students to discuss the understand the current research trends in promoting mathematical research and applications. Physically, for high-profile international mathematics
Dr. Malik Zawar Hussain, Chairman, Department of Mathematics, Punjab University, to chair this session.
Yeah, good morning.
Everyone. So it's my pleasure to introduce Dr. Eric Dolores. He did his PhD from Northwestern University, America, USA, and currently he is doing his postdoc at University of Yonsei, Seoul, South Korea. So it's my privilege because this is my friend. I met her in Mexico, I think 12 years back, when I was doing my postdoc in the University of uh, Mexico City. So I welcome Dr. Eric to present his work, and title of the talk is Order Series. So I welcome.
I want to talk about a combination of ideas from numeric combinatorics, mathematical physics, and applications to number theory. So the main result that we have is a new proof of identity by Ramia. I think we don't know there is this famous notebook in which he is giving a lot of statements, but it is not the proof. And people don't know if it is the because they were very expensive or because he really wants as an addition from England to install this system. Or maybe because currently he is studying with a book that only the book didn't give the proof of the same topic was trying to imitate the style of it. And so we are going to use this notation to represent a concept. It's a little concept because so let's say you have gone to a student of language and math, and then you have Andrea, a student of math and economics, and then you have Luis, a student of economics and history. And assume that Andrea has better grades than Robert in mathematics, and Andrea has better grades than Luis in economics. So, Luis and Robert because they don't share projects. So this is an example of a partially order set, a set in which sometimes you cannot compare two elements. And so we study partially of possess, and on possess, we have separation of units. The idea is that if you have a possess, let's say, for example, this is called create element. It's a graph where I put an arrow between an element and the successor. And so, for example, this arrow that I'm drawing here is the same as writing x smaller than y and x smaller than w. So this path I'm going to run. And so if you have one possess and let's say you have this other possess, here is x smaller than y, then the distribution of possess is considering a total set, but there is no new order relation. So this is the decision. I'm stating the union of them. And if you have the definition as set, you just have elements that can be comparable using the order of P or the order of P. We also have a relation called the order set. And in the case of the order set, what we do is we make every element of the set on the left is smaller than every element of the set on the right. So I want all of these to be smaller than all of this. What we're doing is to take the maximum of these elements and make them smaller than the minimum. So I take the maximum here, I take the minimum here, and what I obtain is the product. So the ordinal sum is a new poset in which, besides the original order relations, I'm forcing any element here to be smaller than every element here. And for example, if you have a set and you do the order sum or concatenation, you have added a new unit. And a significant set is a set obtained by a derivation of these two operations. So, have you ever, I don't know if you ever thought about what is, you can take a random tree, and maybe one of those trees that are in the outside, and instead of the leaves, you can put a drop of water, one drop of water. And when you do that, whenever they reach the drops of water are added, the ground, and so now you have two drops of water, and here you have three drops of water, and at the end you have six drops of water. That means that if you take a random tree, this tree is somehow related to the operation of addition, and in particular, choosing of a tree as a way to put parentheses as a way to iterate the operation of addition. Instead of this tree, I can also give you this order operation, and this is equivalent. And in fact, anything that you see outside is a different representation of different ways to make addition. The advantage is that if you want to study the operation of addition in abstract, it's very complicated. What does that really mean? Well, I can tell you, why don't you study binary trees that have a label on the vertices? Then every binary tree is giving you a different way to compose addition. So binary trees are very convenient because they allow us to study operations as an object. Here I'm not saying we are numbers, I'm not saying complex numbers, I'm saying the concept of operation can be studied using binary trees. And I want to use this to explain what is a series parallel procession. So now concatenation or disjunction. For example, this tree, instead of a drop of water, I used to put a poset in the leaf, and that means take 2 points, concatenate them, disjunction with 1 point, concatenate with 1 point. So this tree is representing this poset, and any binary tree that is labeled with concatenation of disjunction is a representation of a poset. For example, here I take 2 points, concatenation with 1 point, and then here I take 2 points concatenated, disjunction with 1 point, disjunction with everything. So this poset is represented by this tree. And then a series parallel English referee. And these two very different families. The first one is called split, and the second is split, which possess. Now, this is, a lot of set theory, but we can have a geometrical point of view. So, to every possess, we associate a space, a polygon. The rule says, to a 1 point, associate the interval, 0, 1. To a 2 point, associate a triangle. This is a triangle. A point, I have possess, and I have polygon. And so a point is associated to the interval 0, 1. This is associated to, actually, to this triangle, x, y, where x is smaller than y. And in general, there is a formula to obtain the geometric figure, but it's not very likely. It says take every point in the poset, consider it as a coordinate in array, and look for the points that satisfy the inequality. Like here, this point x is this dimension, this point here is this dimension, and then I look for the points that satisfy the inequality x is smaller than y. So then we have a geometric object. We can see by iteration that the n simplex denotes the possess 1 is smaller than 2 is smaller than 3 is smaller than. So the k simplex is mapped to the k simplicity set. Like here, I have a point, line triangle, with 3 points goes to pyramid, and so on. So the k chain goes to a simplicity set. And in polygons, we have 2 operations. One of them is called the free sum. So what the free sum does is you take one polygon and you put the other one, and then you just put all lines between them. So in that example, I have the triangle, which is the polygon of the 2 chain, and I have the polygon of 1 chain, and then I connect them. And I obtain a pyramid. So the triangle is a polygon of a 2 chain, and the line is the triangle, and the line is a polygon of a 1 chain. So a point and a 2 chain give me the pyramid. So I have this free sum of polygons, and there is another operation which called the Minkowski sum. So the Minkowski sum, it just takes the sum of the pair of points. Oh, by the way, this is a typo. It's the sum x equals y when x is the first poset and y is in the first polygon and y is in the second polygon. So in the picture that I draw there, what we have is the Minkowski sum of the line, which is the polygon of a point, Minkowski sum with the triangle, which is the polygon of a two-chain. So we have two operations on polygon, the Minkowski sum and the free sum. Now, the first maybe surprising thing is that if you take two posets and consider the disunion of posets, is the same as, when you compute the polygon, is the same as computing the polygon of each one of them and applying Minkowski sum. If you take two posets and use the ordinal sum and then compute the polygon, is the same as computing each polygon and then the free sum. So something is happening here. I have these posets with two operations, and now I have these geometric objects, my polygons, and the operations are compatible. Something is happening here. Now, let me go to an algebraic point of view. So, define this symbol as the power series x over y minus x to the k plus 1. If you are familiar with combinatorics, this is the Ehrhart polynomial of the k sequence. I'm sorry, the Ehrhart series of the k sequence up to a constant. And on this element, let me define the concatenation by multiplying the power series times y minus x over x. And if you do this, you find that the power series of the k chain with this multiplication with the power series of the n chain gives you the power series of the k plus n chain. And we also define the disjunction by this tricky formula. However, the reason why I need these two formulas is because, and this is one of our theorem, if you define this operation of chain this way, and you define this operation of disjunction, you obtain that the power series of the disjunction of possess is the operation applied to the power series of the possess, and the power series of the concatenation of possess is the previous operation applied to the power series of the possess. So again, the same, how these formulas from possess were now applied to polygons, and now they are applied to power series. So these three objects seem to have the same algebraic structure. In particular, we show that if you take some possess, then you can always write the power series as a sum of some integers and the power series on chains. So, for example, you take this possess, you take so far what we have is in possess, I have the ordinal sum and disjunction. On polygons, I have the ordinal sum and disjunction. On polygons, we have the free sum and the Minkowski sum. And now I'm saying that on all the series, on this power series, in the case of possess, you have the k chain, which is 1 is smaller than 2 is smaller than k. In the case of polygon, you have the k simplex. And now in all the series, we also have the concatenation. This formula says that f concatenated by g is f times 1 minus x over x times g. And we have this operation that was defined using binomial coefficient. And here, instead of the k chain, we have a zeta plus of k which is x over y minus x to the k plus 1. And again, we are saying that there is no compatibility because you can take a poset and compute the disunion and compute the power series, or you can compute the power series of each poset and apply this operation. You can take the posets and apply the ordinate sum, and then or you can take the power series of each poset and then apply this complicated expression. And this will give you some compatibility. And actually, we prove that if you have a poset, so let's take, for example, here I'm going to take this poset, this is given 2, and then you compute the polytope. In this case, the polytope that corresponds to this figure. And then you compute the power series. The power series that we have here, the power series is going to be 3 theta plus of the chain. So explicitly, the power series is 3 x over y minus x to the 4 minus 2 x over y minus x cubed. Then this coefficient 3 is telling me that I can split this polytope as a union of 3 pyramids. And I have here the picture. In the picture, you see how there is one pyramid here, one pyramid in the middle, and one pyramid in the outside. But these 3 pyramids have to share 2 triangles. So the coefficients of the power series are giving me combinatorial information of the polytope, and both of these are parameterized by a poset. So to show why this is not completely trivial, let me give you an example. Consider the portrait, this poset. So I'm saying x is smaller than y is smaller than c, and x is smaller than w is smaller than c. To compute the polytope, then I need to look for the space of points that satisfies these 2 chains of inequalities. But this means in 4 dimensions. And so something I can check is that x is smaller than c, is smaller than 1. So I have a triangle, there is no triangle, and for every point on the triangle, for every point that you pick, you have a comma b, you have a smaller than y comma omega smaller than b. So for example, if actually, my triangle is always diagonal. So if I have here I have 0, comma 0. So omega comma b are smaller equal to 0, so it's a point. Here I have 1, comma 1. So omega and y are smaller equal to 1, so there is no point. Here I have 0, comma 1. So both are bigger than 0 and smaller than 1, so I have a square. And here in the middle, I have some small square. So at every point, I have something two-dimensional, but something discolorized. And this is very hard to imagine. But if instead now we compute the corresponding order series using the formula that I gave you, what we obtain is that the order series of this poset is equal I begin to one minute. Okay. So what this is telling us is that this object that we cannot visualize is a union of 2 force indices. You take 2 force indices, but these 2 force indices share a pyramid. I cannot see it, but I can compute as implicit the composition of the object. Now, there is this zeta function. It's very important in mathematics, but but it's also very complicated to work with. For example, we know that theta is irrational. We know that at least one of these four numbers is irrational, but we don't know which one because it's hard to compute. So we know one of them is irrational, but we don't know which one. Still, uh, let's define now the number. So we have possess all the blocks. If we have series, and now we define a number theta theta n of k to be theta of k plus 1 with operation. This operation come from the operations on our series. They were the same as before. You have a k chain, you have an h chain, and now you have a k plus h chain. You have a k1 disjunct union, an f1, and you have this substitutable sum because it's a number. And so when we're